This is the part where you in the audience get to participate and ask any and all questions to the speakers here about their implementations, trade-offs that they may have made, any questions related to any of the topics raised. If you could come up, there are microphones on either side that you can use to ask questions. So we've got our first question here. So please state sort of who you are, where you come from, and then ask your question. And if it's directed to everybody, say that, or if it's directed to a particular person, say that as well.
Okay, Justin Simmons from Hewlett-Packard Enterprise, directed specifically at the blockchain speaker, Greg. Bitcoin obviously is not necessarily blockchain itself, it's just implementation of blockchain, one implementation of it. But Bitcoin has run into a number of scalability issues. About a month ago, 6 weeks ago, they had this 48-hour delay on putting blocks in there. There's been some articles written that if it were doing the same rate that Visa was, you'd be adding anywhere from 11 to 30 terabytes a month. So it seems with this ongoing infinity blockchain that at some point it runs into scalability issues. I see what you're doing here for the limited nodes, but you'd still have to have enough full nodes to get this agreement. So what's the long-term vision of blockchain in that for those aspects?
Yeah, so that's a great question. And so just to clarify, so the delays or scaling issues that you're actually, the first part of your question, so basically the way that Bitcoin is set up right now is that each block is actually capped at 1 megabyte. That's just a coded in number. It is theoretically adjustable, but it would take what's known as a hard fork of the network, so a non-backwards compatible fork of the code. So that has been a contentious issue, but remember each transaction is, it's just a small amount of data, right? And so if we cap the amount of data at 1 megabyte per block, that means that we're inherently capping the number of transactions. So blocks were not getting confirmed any slower, but if you were not adding fees to your transactions, you're going to be lower incentivized by the actual network processors to be included. So that is actually, so it's actually fundamentally the way that Bitcoin was designed, that it has this fee market native to it that says, if I really need to prioritize it, I can get a miner, one of the processors, to actually prioritize my transaction by attaching more money to it. But you're totally right, is that there's a lot of controversy around should we just raise the block size, et cetera. Now the other side of that, of course, is what happens longer term if we want to go to 10 megabyte blocks and let everybody get all free transactions, then what? So a couple things out of that. There are a series of optimizations around the way that data is stored so that you don't actually have to store everything indefinitely. One of the big advancements that's happening right now is actually around separating out the signatures and the data. And then what you can do is, so I showed basically the Merkle tree of the actual messages. What they're actually implementing is a separate tree for the signatures, so you only have to store a hash of all the signatures up to that point. I mean, you can prove cryptographically that all the transactions up to that point are valid. So that alone will reduce by roughly half the amount of data that has to get stored. The second is that you can actually prune data. So things that have already been respent, you can actually say we can reach agreement that up to this point, all of the transactions at this point are valid for, say, 1 Bitcoin. I don't really necessarily need everything up to that point. I can actually prune that and go forward. The third is that the question is largely around, is it supposed to be like Visa, where I use it to go pay for a cup of coffee, or is it supposed to be a base settlement network on top of which other systems can be built, do all sorts of other optimizations for scaling, and then use it as a final settlement mechanism, which still much more efficient than other networks, but if it's append only, it becomes pretty difficult. So, yeah.
Hi, Gokula Misra from McDonald's. This question is for LinkedIn team. I like the idea of pre-computing some of your structures, but one of the questions I have is what's your point of view on if you have 5 to 10% of the data getting restated?
Hello. Could you repeat the last part of your question?
if 5 to 10% of the data that you are getting in a streaming mode, they get restated, meaning they get changed. They could be either told to be dropped or the value changed, or even added more records.
So you just to clarify the question, your question is about restatement of like certain percentage of the data?
Correct. It happens quite a bit in the financial transactions, for example.
Yeah, so the use cases that we see, so most of at least the tracking data and even the change logs, I mean, they get represented typically as immutable data sets, right? Especially, that's certainly true for tracking data, not completely true for the database data, obviously. And there's two kinds of restatements that we typically see in the end-to-end pipeline. And if you're computing something real time, that's definitely an issue. The two common cases that we see is one, they're just bad data, right? There is bad data that got emitted upstream, and there's not much you can like do other than like clean it up. And the second one is, I think probably more common, is late data arrivals. Now for the second one, there are different stages of audits that's built throughout the pipeline. So at least you have an idea of sometimes how much completeness there is in your processing before you move forward. And there are definitely cases where the computation, depending on its choice, could choose to move forward if it's, say, 99% complete, versus other computations could choose to wait until you have, say, 4 nines of completeness, for example. And I think the restatements also generally follow that pattern of you have some late data that shows up in, say, last day's data. Then you could choose, depending upon how much late data that you have, to re-trigger the computation or not, right, depending upon how strict you want to be. And the same goes for like bad data. It's really about how much bad data that you have and whether there's not much you can do other than clean and reprocess the entire data set. And it again depends on the percentages that you see. So this is a common pattern where I think the Lambda architecture comes into play again, which is there are a lot of places where we do real-time computations, and you could say, okay, this is the metric value that you see in this particular 5-minute window or an hour, but depending on the other issues where later on we see this reconciliation, we usually use the batch pipelines to correct things and then restate the results.
And the only thing I would add to that is the pre-computed indexes as well as the data is kind of in immutable segments, and they represent a fixed block of time. So you could actually compute them separately using the batch pipeline and kind of replace the whole thing. So so it's not like one tree that is sitting there getting real-time updates. The trees also close out after a certain amount of time.
Okay, Martin Kersten, CRLI Amsterdam. I have a question for the blockchain. How do you avoid starvation? Because there's no guarantee that your complete system will actually fall apart by not actually being able to reconcile actually missing actually blockchains. Except by stopping the system, which is a distributed system, waiting. So how do you avoid starvation?
Sorry, can you repeat the question? How do I avoid starvation?
How do you, well, if actually two systems actually doesn't agree on the hash, so you're going to back to try to figure out the one of them. While you're doing it, actually the other one may create actually another inconsistency, and actually the two systems may never actually reach an agreement, and may end in a ping-ponging situation, and it's becoming aggravated if you're in a distributed environment, where even subsystems may actually not be available at all. So your system can actually comes to a concrete crash, and especially, of course, in the financial market, it will typically happen when the market is as the utmost need that there is actually synchronization.
Yeah, so one of the pieces that I didn't touch on during this presentation was around consensus mechanisms. So consensus is basically, how do you determine, when you're creating a block, how do you actually get to the point where you can agree on, what is the actual state, how are we going to update this checkpointed state together, right? So pretty much all implementations get to a method of a single party doing that, right? So in the case of, for example, Bitcoin, you have miners that are competing to do, well, they're actually very basic calculations, but taking a bunch of random guesses, and then whichever one finds it correctly is the one that has the authority to add to that list whatever the messages is that he wants to include, he or she. And then all the other nodes are basically going to validate the format is correct and that the cryptographic signatures are correct. There are a ton of other consensus mechanisms that are now getting deployed, so you can actually do things like rotational consensus, where there's a single party and you go around in a ring and say, we're gonna go 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. But when this consensus is actually getting made, it's usually determined by a single party, and then other parties then reconcile against that sort of timestamp period. So that's a more complex answer. Yeah.
Frank Olkin, currently at my own consulting firm, recently National Science Foundation. My question is for Prabhat. So I'm not familiar with the most recent configuration of the LBNL, the NERSC supercomputer configurations, but traditionally these machines have had major investments in the switch, that is the switch connecting all the processors, had very high bandwidth, very low latency, very expensive, and they had segregated disk storage. That is, instead of putting the disks on each processor like they do at Google and places like that, they put the disks off to the side, connected through some sort of high-speed net. And the other thing is, traditionally these systems have been optimized for very large workloads and given their top priority to the biggest jobs. So, and batch, basically. And they were run, as you mentioned, at very high utilization rates to justify the large expense. So now you've got configurations where you're trying to build more interactive workloads, real time. Traditionally, the way you get low latency on real-time stuff is you decrease the effective utilization. So your servers are not really busy, because we know when you have busy servers, you get long queues. So, and the other thing is that traditionally the supercomputers have had somewhat exotic or unusual processor configurations and relatively limited software configurations. Maybe they'd support Fortran and C, but not lots of other languages. So my question for you is it really economic to run these kinds of workloads, particularly the data-intensive workloads, on these machines that have really been optimized more for compute applications, because you've got a big investment, because the Google things don't have the kinds of switch bandwidths or latencies that your configuration does, or the expense. They're cheaper, essentially. And the other question is this sort of politically feasible, in that you really have two very different constituencies here in terms of what you're trying to do? My impression from listening to your talk is that what's going on is that you're trying to reduce the costs of maintaining multiple software stacks and institutions in terms of people, and by collapsing all these things onto a few configurations. Could you say more about this?
Sure. So, economically, again, if we are federally funded, our mission is to support science, and if much of science is going to be data-driven in nature, then we'd better make sure that whatever resources, hardware or software that we provide, are responsive to the needs of the community. I think there is, so I mean, I agree that the data center hardware has a different trade-off, has a different point in the trade-off space compared to HPC hardware. There's a lot that we can do in terms of improving the conventional commercial big data stack on our systems. Frankly, I don't see why we can't get that to run well. So I think we've started some of those experimentations. We're looking at Spark, and we are characterizing what the performance gap is between Spark and the conventional HPC languages like C and MPI. Vendors like Cray and Intel are starting to work with us on optimizing the big data stack. So I think, I don't think NERSC is unique in that position. I think you're going to see some of the roadmaps from Intel and Cray start talking about the convergence of hardware and software architectures as well. So that's coming shortly. Certainly, so I think there's a bunch of work that needs to be done, and for me, I think the challenge is in software. Hardware is what we have at this point in time. I'm not convinced that the big data software stacks that we have running right now on HPC machines are in any way optimal. I think we are off by at least an order of magnitude, if not more. Does that answer your question?
I think I'll follow up offline.
This question is for Greg. I'm Carlos Gamboa from Brookhaven National Laboratory, and I'd like to know what type of hash functions you use to generate the hashes.
Yeah, so the Merkle trees that I was showing up there, so you're generally going to, when you're concatenating, and then you'll do a double SHA. So SHA 256, SHA 256, and then you do that over and over again. Now, there's actually just one more clarification on that. Within most blockchain systems, there's actually a ton of different hashing functions used for different things. So we can chat offline, but like just to give you an example, Bitcoin mining are searching for a nonce to create a SHA 256 hash. You have another one called Litecoin that uses script. You have like if you basically you're optimizing for basically how difficult is it to create these things, and what is the intended protection for various systems. But the one I was showing is double SHA.
Julian Hyde, Hortonworks. This is a question for Greg, or in fact anyone on the panel that wants to take it. So there's a well-known property called stream table duality. A stream is just the changes to a table, and a table is just the sum of the records that are flowed over a stream over time. And users tend to find tables or databases a convenient metaphor for most things. In the case of distributed ledger, some users would like to see this as a database, a form distributed database, because it is a distributed transaction log. So my question to anyone that wants to answer it is to what extent are these systems going to end up just looking like databases to their users over time? And to what extent are people going to need to deal with data in flight, deal with stream processing? Is it possible that over time, fewer and fewer users are actually dealing with streams, and most people are dealing with a database as the abstraction for these systems?
Yeah, I can actually. So the short answer is that there is no single answer, and it really depends on the context of the implementation and the use case, right? So if you have a single entity that for whatever reason custodies or processes a lot of transactions or manages order books or whatever it might be, and the objective is always going to be to synchronize against them, then yeah, it starts to look a lot more like a traditional database. Even if you're using a Merkle tree structure and helping end user synchronize against it. However, there are a ton of other more distributed markets. There are markets with the example I showed had a central infrastructure provider, but there's a lot of markets where that doesn't actually exist. And what you literally have is end users that actually have individual copies, sometimes still on paper. Those are the places where we start to see a much more distributed network where it doesn't look like just connecting better to a central database, but you actually end up with so in the CDX example, for example, we actually had a proper distributed network where it was very similar to the types of concepts you would see in a public large distributed network like on Bitcoin or something.
So I think there's definitely, a lot to the point that you made, right, where I think, and we're seeing a lot of cases in our world as well, where, through, especially like event data and time series data, where I think we get closer and closer between, what traditionally we think of as databases and what traditionally you would think of as streams. And, I think the important thing there is probably having that logical notion of a stream and how effectively you can implement it in like different like physical deployments. And if you look at what we're doing in not only for our batch data but also for things like Pinot, where I think the concept of time series naturally flows through because a lot of it is immutable. I think you can actually do a lot of what you would consider just like stream processing functionality much closer to where the data is actually then stored within indexes and so on.
Yeah, I think what tends to happen is we're seeing very little of the traditional, I have a bunch of data and I'm going to query it. It's mostly window-oriented processing. And so that's really the key. And whether that window translates, that the processing on that window, if that translates to literally scanning every tuple as it comes in, or essentially pushing down that query against an engine that has the data organized and is fast enough that it can actually operate on that query faster. You basically are trading off the immediacy of the output tuple with the cost of organizing the data so that you can query it faster. And I think what we're seeing is kind of the streaming systems and the analytics databases kind of converging because streaming systems very quickly start realizing that the processing is just one part of the story. It's really the getting it to the end state where it then gets queried that's kind of more important. So I think the last mile tends to be the most interesting one for stream processing, where data is finally getting ingested into the serving store. And a lot of the serving stores are actually embedding stream processing into the ingest layer. So something like Pinot, for example, is essentially stream processing data as it's coming in. The data structure that we talked about, which is the kind of the data-aware tree, is actually getting assembled as the data is streaming in. And so as long as you don't need, and you tend to kind of have shuffles and other things externalized, but as long as you're in a distributed system, as long as you're bringing in the partition of the stream that you're responsible for serving, you can do actually a lot of interesting things at ingest time. That is kind of almost has the best cost to serve trade-off for what you're trying to do. So I don't know if that really answers your question, but I think a lot of applications or pipelines first skew towards let's segregate processing and serving, and then realize that a lot of the processing is getting bottlenecked in just getting the data out from the processing tier into the serving tier. So then you see some of the processing moving back into the ingest part of the serving tier. So we're seeing a ton of that. Things like real-time temporal joins, where you're taking multiple streams and combining them to create a unified view across those streams. So for example, when you interact with a page, there are multiple events that are firing. The first event when you requested the page, and then as each individual widget loads, there might be individual events that are firing, and there's a little ID that is tacked onto each of them. Now when you're representing an analytics query against it, you want all of that data kind of to be represented as if it's a large event instead of all of these small breadcrumbs that were dropped. And so those kind of use cases definitely need like this little stream processing layer right in between to kind of create the wider event. But once you have that, then I think the serving engines are pretty good at organizing it in such a way that you can query it real time as fast as you can get to it.
So I think in the world of science, it's always going to be a collection of technologies. Again, many communities have long decades worth of traditions in using a certain storage solution and whatnot. So the high energy physics has used Root for 3 decades. Climate folks use NetCDF, and I don't see them moving away. So anyways, I think when it comes to NERSC and we think about data management solutions, databases are certainly a part of the conversation. Conventional I/O libraries like HDF5 and NetCDF are a part of the conversation. We are starting to think about streaming extensions to HDF5, but those aren't quite there yet. But I would say I think the notion of stream processing, as is implied in the industry, I don't think that's there in the science world yet.
Hi guys, all of your talks were really, really great. Thank you for those. My name's Tim Frazier, I'm from Oracle, and I'm gonna take advantage of the lull here to ask 2 questions, so you have to remember the first question while you're thinking about the second one. The first one, I think, is mainly to my colleagues at LinkedIn, and it is this. When you're ingesting so much data, have you made a provision to have the concept of a high priority channel? In other words, to let some data maybe sneak by, the droves of other data that you might be getting. And then the second question might be for all of you, and that is how important to you, if at all, is the ability to purge data to maintain the performance of your systems? And we had very vigorous debates last XLDB about, do we keep data forever? Do we purge it? And so I would be interested in hearing a little bit about that. Thanks. So first question is high priority data. Second is data purging.
Sure. So we've done kind of a coarse prioritization of data at LinkedIn. I'm talking primarily about the stream data. Database changes are also regarded as a stream, obviously, right? So those go into kind of their, and the way the prioritization has just been done is just through isolation. So there's a separate cluster for what we consider database changes. There's a separate cluster for the tracking data, which is what I talked about in my presentation. And then there's other kinds of stream data as well. The machines, the services are all actually writing out the traditional logs as well, just log4j messages, which are also getting streamed through Kafka. We also have monitoring metrics exhaust coming out of containers and other kinds of processes, which are also getting streamed to Kafka. And generally, we've segregated those clusters. So that's kind of at the macro level, where people kind of know that database data is special, that tracking data comes very close second, and that everything else is kind of in the third bucket. And so that's kind of a simple way for even operations to kind of realize or deal with failures, right? They'll react much more quickly or with much higher sense of urgency if one of these higher priority clusters are down. Where we've seen a lot of challenges around prioritization are on the ingest side. So Goblin, for example, ingests pretty much all of this data into Hadoop, and some of this data powers critical dashboards, and some doesn't, right? So even if we're getting data from the tracking cluster, there could be an event that is super critical and is getting reported on very quickly, and Jeff is looking at it. Whereas there could be some other event that is not that useful, but it's much larger in size and sometimes can tend to clog up the pipes. What we have, I don't think we have completely succeeded at it so far. What we've done is kind of a more like metadata-driven approach where given a data set, you can go in and change its priority. And so there's kind of a way of assigning tiers or priorities to data sets. And these multi-tenant ingest pipelines are able to kind of isolate themselves and only pull the high priority stuff. But still, the thing that's missing right now is kind of the automatic detection of what is important and what is not. Today, it's still manual. We have a lineage graph, and I didn't get to talk about the metadata system. It's pretty cool. We do have a lineage graph that allows you to go right to left and go from a downstream dashboard or a data set and kind of see what are the source data sets that are powering it. But today, we don't automatically propagate that metadata. We look at it and say, oh, I guess these data sets are important, so operator, go in and make those high priority. What we want to work on, obviously, is being able to automatically bump up or down the priority of data sets based on the criticality that might be established further downstream. So that's kind of the ingest piece. And
Prabhat, do you want to take a chance at the ingest piece? Because I think you're doing some prioritization there as well, right?
Well, I guess prioritization we think of it as a user space problem. There's a finite amount of allocation you have. Based on the number of compute nodes you get, that's the amount of memory. You have a certain amount of space on your local file system. And, I mentioned the burst buffer, so that's an interesting technology that you can certainly bring to bear. So certainly get a hold of how much burst buffer resources you can. And now, related to the purging question, we have hundreds of petabytes worth of data on tape. So we don't purge stuff. We purge stuff on our Lustre file systems and so on, but the tapes remains untouched. The tools regarding automatic prioritization don't exist. We see the storage memory hierarchy deepening, and frankly, the tools for moving data between the file system to the burst buffer to the memory are completely lacking at this point in time. So I think going forward, that is certainly going to be an open area for research, and And again, I think all vendors are looking at that right now.
I think actually on the purging question, so if you think about the context of financial markets, one of the things that's really interesting about this technology is you have basically an inherent logging system, right? It gives a full audit trail of not only, you can see not only the current state of a contractual agreement, but you can also see the full audit trail and history of how you got there, which means, for other data systems where you might overwrite something, in this case you have natural logging, right? Not that came out wrong. You have inherent logging of the system, right? So from a financial institutions context, that they're saying that's incredible. From regulators' context, they're saying that's awesome. Every message is cryptographically signed. That's great. So purging that is not really a priority for the period that something is active. So you might have I gave the example of credit default swaps. You're looking at an average term there of about 3 to 5 years. So you're going to want to keep that data around, particularly because an update to that contract might reference it in the future. However, by the time you get to the end of that contract, by definition, it's not going to be acted upon again, which means that you can, purging is kind of broad term, but at least archive it is certainly something that can be done, so that your node doesn't have to constantly query against it.
Yeah, to chime in on the purging data, so it's actually rather interesting depending on sort of the kinds of data sets and the use cases, right? We have like a variety of different data sets. I mean, some are obviously much more useful only in the very short term, and as the time progresses, you're like, okay, like you don't really need to go back more than say a month or something like that. And then there are other data sets which are, could be much more useful, and you would want to keep them as long as you would want. But then it depends on like what kind of data you're allowed to keep and for how long. There are certain data sets that you're not allowed to keep for more than certain period of time. There are other regulations which dictate what you're allowed to sort of keep and what you're not. Typically, if you have a user that closes his account, then you have a short window of time by the time which you have to get rid of like any evidence of their activity and so on and so forth, right? So, system and at a system level, systems that usually keep a low or a rather small window of retention, it's easier to deal with because data is naturally getting purged out as time progresses. Systems for batch processing like Hadoop and so on, where that's generally sort of your like the data warehouse where all of your data is accumulating, it becomes much harder and much more interesting to enforce all of these different purge policies. Time-based is generally the easier one, right, where you can just start dropping old partitions. But anything that is more sophisticated in terms of like, maybe you're allowed to keep certain fields but not others, and those become a lot harder to implement.
Frank Olkin Consulting. My question is for Greg Shea. So what you talked about mostly and all the Merkle tree stuff is agreement on the bits. But the bits encode contracts. And the contracts contain terms which have legal definitions and other things like this. So my questions for two related questions. The first is, to my knowledge, these derivative contracts are 300-page documents written in English. And as far as I know, there are not standardized machine processable representations of these things. In fact, there's even ongoing debates as to the meaning of many of the terms. So one, could you address that point? And two, the securitized contracts are dependent on thousands or tens of thousands of mortgages. And the state of those mortgages, as far as I know, is not public. So in terms of looking at this in terms of systematic risk assessment, how are you addressing, one, the semantics of the contracts and machine processable contracts, and two, the underlying basis of the state of the mortgages?
Yeah, great question. So I guess I'll start at the simplest and go most complex. So there are actually a series of, particularly in the derivative space, there are a series of standardizations that have happened. So just to continue off the example I had before, credit default swaps have what's known as the standard North American contract, and they also have indexes that are composites of those contracts. So those are fairly standardized. However, you can get into a series of other more bespoke sort sort of contracts. You could have equity portfolio swaps. You could have bespoke swaptions. These things are basically, there's a series of different things that you can do. So what you can do with a smart contract is multifold. One is you can create a template such that you can swap in or out from a matrix of potential options, right? So if you're buying Apple equity, share 1 is the same as share 476, right? 2 swaptions might have a ton of different terms and options in them. However, the total matrix of potential options is actually fairly standardized. So you can actually build a template that draws and chooses from those. The second is that third, there's an entire body of work right now, and we're working on this with some of the firms that we're collaborating with, particularly some of the larger banking partners, around actually taking legal language and tying that into the actual smart contract. So the smart contract is always going to be a representation, but what you can actually do is say, okay, this points to certain legal language. There's an entire format within the financial industry, XBRL, which basically is a standardization of legal documents. So we can actually pull out the relevant terms from that, turn that into smart contract language, and then reference the actual document itself, and then create, the things that have to be automated and processed. You can actually do by drawing from the actual legal contract. The fourth, I guess, is that again, we're talking about a Turing complete language on top of this network, which means that should you want to do something utterly bespoke, no template fits, no nothing, it's a matter of reaching agreement on the code base with that counterparty. So that is a layer of work, but whether lawyers or developers are more complicated to work with is anyone's anyone's guess. And getting them to work together is probably a whole new set of work. But and then the final one around the mortgages is that what we're really talking about is you don't actually have to have the nuances and details of every single asset. What you have to do is have details around a representation of a mortgage, right? And basically saying, so I have the trade details or whatever the actual details are of a mortgage. You can have internal to the underwriter and have those actually represented on a network in another way where it says, okay, if you ever want to find the original document, it comes back to me. But in the meantime, you can take the economics of it and package them up. So a lot of those, you can package up into a public network without exposing a lot of that data.
Yeah, follow-up question?
But my understanding is that the state of those mortgages, which affects the state of the derivative, is not public. It's internal to the mortgage servicing organizations. Is that changing?
So there's a couple other components that we would have to get into around. So in a standard, like if you're looking at something like Bitcoin or Ethereum, these are inherently open and public networks. The implementations that we've done in capital markets are not all data is public. So data is actually restricted to where it gets shared. So it's a whole other topic we can talk about afterwards. But the nuances around this is more around the way the data is shared and what data even makes it onto a chain in the first place.
My name is Ashish Mahabar. I'm from Caltech, and I work on real-time classification of transients, including on surveys that Prabhat mentioned, PTF and LSST. My question is more general for real-time processing, but I guess it involves tagging, restating of data, and perhaps backpropagating. With LSST, we are likely to find millions of transients every night, and they will be tagged. But overnight, there'll be better processing, and some of them will be discovered to be not really transients. But some people may have gone and done follow-up on them. And that may be partly through push, pull, various kinds of mechanisms. So how can one rein those back in? How should those tagging be happening and related to that?
Well, some people in my group, Roland Thomas and others, have worked for a very long time now on designing, an integrated workflow for enabling this kind of decision support. I'm not sure if those are going to hold up at the level of the LSST. And I would hope that folks at the NCSA are thinking about that. So yes, I guess I didn't quite understand. What are you talking of a scaling challenge, essentially? Scaling it to millions of objects, is that the problem? Or which hopefully machine learning will address to some aspect?
Yes, so partly it is scaling, but also when some events have gone out and people have been following those.
Mm-hmm.
And then later on, if people do searches on similar types of objects, those that have been now discovered to be not transients, there should be a proper tagging mechanism so that newer people don't find that, and even people who have been finding them, who had found them before, realize that those are not transients worthy of follow-up. So
That's
more
right. So
bookkeeping kind of thing.
that's right. So I think ideally there would be a shared knowledge base of some kind that is updated and accurate, which reflects not just your subtraction and machine learning based classifying system, but also follow-on studies and tags that might have been refined. I don't know if those systems exist right now, but clearly that would be worthwhile. Mm-hmm.
Yeah, sure. There are various things that need to be done. Maybe we can talk more about.
Sure.
There's one question that came up during the break that actually, Kapil, you raised that I wanted to kind of raise to the larger group, which is there's a lot of talk in the industry, particularly related to real time, about in memory. If you talk about real time, everything should be in memory and so on. You made very clear that at XLDB scale, maybe that's not always economical. There was a talk by Facebook, I think 2 years ago, where someone asked about in memory, and his response was, well, at our scale, we're a free service, not a chance. I want to sort of revisit that with this panel and have your opinions on, how important is in memory? And when we say in memory, is it 100% in memory? Is it, you hinted that it was not all in memory, but how much in memory? What is the right ratio for the kinds of workloads that you're looking at? And obviously you've got different workloads, so the number may be different, but just trying to get a range.
No, I don't think we've, sorry. Yeah, I think it would need to be in memory for the kinds of workloads that we are talking about. I'm not sure about the breakdown. Frankly, the I/O subsystems are just not keeping pace. So again, if things are on tape, of course, you have no hope. But even Lustre may not cut it. So I think we are thinking seriously about SSD-like technologies, and the question really is how do you get data to the SSDs fast enough, especially if there is an external network. So those are bleeding edge questions as far as I'm concerned. But no, I think if we want to support a real-time analytics use case for data sets which span terabytes to tens of terabytes of data, I'm not sure about hundreds of terabytes, but certainly terabytes to tens of terabytes, then it would need to be in memory. And looks like SSDs may be helpful.
Do you want to expand on your answer, Kapil?
So I think a lot of it goes back certainly to, I think, use cases, right? I mean, if you're doing processing either very close to the source or sometimes in the ingest, you can definitely do that while the data is still in memory, and depending upon the scale of your system and the data, some of the processing might be much more feasible or amenable to doing at that state, right? Now, as the processing typically gets much more complex, it's a trade-off, and how much you can afford to do it, close to the source, or as it is flowing through, as opposed to when it is sitting in cheaper media. I think SSDs definitely, depending on the kind of use cases you're talking about, definitely make a lot of difference. Like especially the closer you get to the OLTP side of things and the serving side. Like traditionally, we used to have much more trouble around managing the page caches, for example, right? Especially when you're serving this low latency systems where you have a huge cliff in terms of performance when your data sets go out of memory, and then you're dealing with, you can't really serve it out of disk, and then it's a question of IOPS. And when you make some of those work on SSDs, there's still a difference between the performance you'd get out of RAM and out of SSDs, but sometimes the degradation can be a lot smoother. So there isn't, unfortunately, one clean answer. It really, the answer is it really depends on the
So for
use cases.
analytics specifically, what is the kind of ratio? Like if you have 1 petabyte of data, how much RAM would you expect? How much SSD would you expect? How much, disk would you expect?
Again, it goes back to, I think, a lot of the use cases, right? I mean, if you're doing machine learning type workloads, right, and you would see, or any iterative computing workloads, for example, you're probably going to benefit much more out of boiling that data down, keeping it resident in memory, and then iteratively computing on it. If you're doing traditional ETR workloads, you probably are not going to see as much benefit. So you might want to live with a lot smaller ratios compared to what you would see in the other worlds. I think when it comes to the OLAP serving type of systems, the ratios tend to be like a lot smaller than you would find like otherwise, but there are a lot of work that's going on, some work that we are doing in systems like P&O and otherwise that are constantly sort of stretching those limits.
For blockchain, any opinions on that?
Again, it depends on the market and what you're trying to do. So I'm thinking of most derivative assets are not traded that heavily, so it's actually the bigger thing is going to be synchronizing against other parties. The memory cost is not going to be that high, but you're also not doing. I could probably define a few dozen primary queries that are going to be most of the analytics that firms are going to want to do on these types of assets, which means that I can pre-index them pretty readily rather than having to keep everything ready to be immediately analyzed in memory. However, I'm thinking of a lot of the work that we do. We take in just a ton of exchange data, which is much higher throughput, much faster. And then if you want to build analytics out of that, that's the kind of thing you want to keep in memory. So we usually dump it after an X period of time back into long-term storage. But that's the kind of thing that if you're looking at anything that would affect active trading, then you're going to probably want it in memory.
I think we have time for one last question.
Hi, I'm Praful and I'm from Teradata. My question is for LinkedIn team. In your talk, you mentioned a couple of projects using Yarn for the resource management. Did you also consider any other resource management framework like Mesos, and how did they compare with Yarn?
So, well, the answer is because we started from Hadoop, and since Hadoop comes with Yarn, and a lot of the systems that I talked about are kind of multi-tenant and running on the Hadoop grid. It's kind of the natural first step to integrating with a resource manager is to just pick Yarn. So Samza made that same decision, and Goblin has also ended up making the same decision. Over time, as these projects mature and they go out into the world, then people start applying them to their own ecosystems. And so I think we've seen the community contribute Mesos support and a bunch of other things as well. On the serving side, LinkedIn has actually traditionally been more just JVM oriented with static allocation of services to machines. But in the last 6 months, we've been working on a project to actually create more of a private cloud. So being able to take containers and run services inside them. And while I wasn't part of the team that did that evaluation, I know that Mesos was considered along with a few other systems. I think in the end, we're going with kind of a lightweight in-house system with kind of the lib container framework as the base for running these things. So.
Okay, I think we're going to extend with.
Can I just make 2 quick comments maybe to wrap up here? I think one is that I think you talked about temporal joining of streams, and I think that actually has a lot of resonance in a lot of other areas. There's you're building to sort of what happens to a particular user as they come to the site, but in high energy physics you have event building where you're trying to figure out what happened in this collision. In astronomy you have to join the image pixels you took with the metadata about the environment, whether it's the atmospheric environment or the environment in the dome or the instrument itself. So I think there are a lot of temporal join kinds of problems that we all have. And then the second comment that I'd just like to make is that it's very interesting that there's a whole spectrum in a way of service level agreements that you have here, all the way from near real time kinds of synchronizations all the way up to batch jobs that can run for minutes or even hours. And the level of reliability that you need to promise to your users kind of varies. I was kind of hoping that somewhere along the way there would be a unified theory of how to do this entire spectrum in one technology stack. But it seems like for now, at least, there's still an art for choosing where the dividing lines are and which tools to apply in which cases. But maybe something like Beam or will help to unify more of these and provide a single environment that we can all work in.
And I'm hoping on Thursday we'll have some discussions around sort of cross-fertilization across some of the different industries and disciplines and so on. So I think we have to break for lunch now. So I want to thank the panel one last time for participating, and thank you also for your questions.